In this section, we talk about the pH effect. When we're saying pH, we're really talking about the effect of either a strong base or a strong acid. The first one I consider is the strong base, and we're talking about magnesium hydroxide with this KSP when we put it in the presence of sodium hydroxide. Before I go through that, take a look and review what happens to magnesium hydroxide in water. It has a solubility on the order of 10 to the minus 4 molar. What's going to happen now when we put in the sodium hydroxide? Well, being a strong base, it is totally going to disappear. It gives us the spectator ion Na plus that we do not consider, but we do need to consider the OH minus. So I've written my KSP equation. I've made my ice table where I am putting in my X's in my change line, and I have an equilibrium line that I can use to do my calculations. So next, I've written my KSP expression. I've substituted in my equilibrium values, and just like in the past, I've ignored my 2x, simplifying it, and coming up with a 10 to the minus 9 molar solubility. So it is a factor of 10 to the fifth more soluble in plain old water. You've seen the calculation. This is just like the common ion. Please take your time and go through it slowly, all right? What about strong acid? Well, strong acid, it is a case by case as we teach Chemistry 1220. Write the equations and think about Le Chatelier. My first equation is the KSP equation, but where did the second equation come from? Well, anytime I have an F minus in solution, it is going to react with water or H plus to regenerate the HF. And that's where my second equation comes from. It is the KB of an F minus. So you're also going to say, where did this number 2 come from? Remember in the past when we were trying to cancel things out, we had to do an adjustment? Well, when I multiply this by 2, I will get a 2F minus, meaning that will drop out. I will get a 2H plus, which I'll put in the reactant slot. I will get a 2HF, which I will put in the product slot. But what I've really gotten is I have freed up the lead cation. So in terms of concept, F minus is a very strong conjugate base of a weak acid, and its net result is to make the PbF2 more soluble in the strong acid. So the bottom line is the solubility of any compound that has a basic anion, by that I mean the anion of a weak acid, the solubility is going to increase as the solution becomes more acidic. We do not do a calculation. We keep it on the conceptual level. So this is the strong acid trend. It's no longer in your text. It was still in my notes. Notice they plot the molar solubility on the y-axis versus the pH. What does a pH of 1 mean? Well, it means a high H plus concentration. So you can see there is a trend. So you no longer go into depth in the book, but this is kind of how it stands. So recapping, strong base, do a common ion. Strong acid, use Le Chatelier. This is kind of the summary of what can happen. Strong acid, PbI2 comes from HI. Weak acid, PbF2 comes from HF. In your text, they show a picture where there is absolutely no reaction. But when we have the weak acid salt and we add a strong acid, just as I've shown on the preceding slide using 2 equations, the net result is this H plus is going to result in the dissolution of PbF2, and that is going to free Pb ion in solution. We can't go into the Flint water crisis, but again, what happened there is free lead ions were formed, which people drank, which can affect your cognitive abilities, okay? What I also put in this section is what I call cation amphoterism, and that is by observation. Please don't say to me, I need to know where it comes from. It is from something people observed, all right? You've learned that amphoterism means you can act either as an acid or a base. There are some metal hydroxides that are insoluble in water, but they will dissolve in both strongly acidic and strongly basic solutions. The ones where they have made this observation are aluminum, chromium, zinc, and tin. These others are not. In the old days, we had a lab where you actually observed it with your eyes. It made it a lot easier to teach it, okay? So there is this picture here. Take a look at it in text. But what I want to do is focus in on the chemistry. The key equation for aluminum is sitting right here, where we have aluminum as a solid reacting with hydroxide. It can also react with H+ and form an aqueous solution. To explain it, aluminum Al3+ is really Al3+ with 6 waters around it. So what happens is we go from 6 to 5 to 4 to 3. And what happens when we hit the 3 waters around aluminum, we have a solid. But notice if we go up to the 4 waters, or if we go down to the 2 waters, we have solubility. And this is the property used to purify aluminum, which is why I put the aluminum cans there. Bauxite ore is a mixture of aluminum and iron oxide. In the presence of base, what happens, it becomes AlOH3, the solid, and it can be filtered out, but when it's retreated, it can go back and form an aqueous solution. The iron oxide does not dissolve it, and I'm hoping Angie has a demo that I can actually show you where this occurs. So this section, 2 things. What happens in the presence of strong acid, strong base? What happens if we have an amphoteric cation?